Hi everyone. Now in today's video lecture we will go through one very important property of compounds that contain transition elements, right? It is that compounds containing transition elements are colored, right? We need to understand the reason why compounds of transition elements are colored, whereas if we look at S block elements or P block elements, compounds of S block elements and P block elements are mostly colorless, right? We'll be looking into the reason why, right? Whenever we talk about color of any compound, right, why a compound will look colored, it's because of electron transition from a lower level to a higher level, right? From a lower level orbital to a higher level orbital, right? So for this transition or for this promotion of electron from lower level to higher level, you need to have half filled or empty orbitals, right? So color is connected to two things. First is half filled orbitals, right? Second is electron promotion from lower level to higher level orbitals, right? So when we say that transition metal compounds are colored, right, we need to find whether they have half filled orbitals, whether electron promotion or electron transition is taking place between the two, right? So the reason why these compounds, transition metal compounds, are colored, it is what we introduced term is DD transition, right? Because electrons will get promoted, the second point, electron will get promoted from one set of d orbital to other set of d orbitals, right? This thing we are hearing for the first time, the different set of d orbitals. We'll see how different set of d orbitals are formed, right? Because till now we have heard that transition metal compounds contain d orbitals and all 5 d orbitals have same energy, they are degenerate, right? We'll see how this concept changes when a complex compound will form with transition metals, right? So here DD transition, right, it is due to DD transition that your transition metal compounds are colored, right? And for this DD transition to take place, you need to have half filled d orbitals, right? Just understand these two things. If you understand these two things, this concept is easy to understand, right? Now let's talk about DD transition, right? First thing, if we talk about a transition metal, right, or a transition metal ion, right, not in a compound but separate, in a isolated, right, then that transition metal, right, or ion will have 5 set of orbitals, which is dxy, dyz, dzx, then you have dx square minus y square, then you have dz square, right? All these orbitals are degenerate. They are degenerate, that is, they all are of same energy. Now let's see how these 5 orbitals, which are of same energy, right, in isolated metal or ion, how these 5 orbitals will split into 2 set of d orbitals, right? dd means this is one set of d orbital, this is other set of d orbital, right? And these two are of different energy, right? Like this. If this is your, this like this, one set of d orbital and the other set of d orbitals, right? And when we say that the color of the compound is due to DD transition, that is promotion of electron from one set of d orbital to other set of d orbital, this is how this promotion will take place, from one set of d orbital to other set of d orbital, right? Now let's first understand how these two set of d orbitals will form. What happens is when a complex compound, right, with transition metals form, what happens is if this is your metal, right, what happens is different atoms or group of atoms, right, will approach this ligand, will approach this transition metal, right, in order to form complex, right. Now group of atoms, right, now these groups of atoms may be negatively charged, like chloride, right, bromide, or maybe others, or they may be neutral like ammonia, right, water, like this, right. So these ligands, when a complex compound will form, right, transition metal compound will form, these ligands, which are atoms or groups of atoms like chloride, bromide, ammonia, water, when they approach this transition metals, what will happen is these ligands have either a negative charge or they possess lone pair of electrons, right. So when they approach this metal ion, right, this metal ion also has electrons in the d orbitals, right. So since they have electrons in the d orbitals and these ligands also has negative charge due to these lone pair of electrons on the neutral ligands or the negative, or due to negatively charged ligands, these two electrons on this transition metal, right, electrons in this transition metals and negative charge on these ligands due to lone pair of electrons or due to negative charge, they both will experience a repulsive force, right, they will experience a repulsive force. Now due to this repulsive force, the energy of the d orbitals in this metal ion will rise, right, energy of the d orbitals will rise and they will split into two set of orbitals, right. So this is how degenerate orbitals, right, that is the orbitals that are of same energy will split into two different set of orbitals, right. It is due to this repulsive force, right, which is between ligand and metal ions, right. So now these will split into two set of orbitals, right. And you have a diagram here that even you can see in your books also, right. This is your energy of isolated metal or ion, right. When these ligands will approach, the energy will rise, right, and at one point these 5 set of d orbitals will form 2 set of d orbitals, right. They will split into 2 set of d orbitals. This is your Eg and this is your 2Tg, right, set of d orbitals. Now your Eg is your dx square minus y square and dz square, and your T2g is dxy, dyz and dxz, right. Now these two are set of orbitals, right, between which this electronic transition will take place, which is your dd transition. These two are two different set of d orbitals, right, and they have an energy difference now of delta, right. And now this energy difference, just remember one thing, is corresponds to the energy of visible region, right. This energy, that is the energy difference between these two d orbitals, will correspond to the energy of the visible region or the energy of the visible light, right. Why I am talking about visible light is because these compounds, transition metal compounds will appear colored when visible light will fall on it, right? So the energy or the wavelength, right, frequency or the wavelength of the visible light should be equal to energy difference between these two set of orbitals, right? Then only this second thing will take place, electronic transition from T2G to EG orbitals, right? So this entire process is known as your crystal field splitting. Crystal field splitting. Right? We will do this once again in detail when we will do coordination compounds. Right? Now you have for DD transition to take place, now you have two set of d orbitals that are formed when a transition metal compound is formed, right? When these ligands will approach the transition metal, the d orbitals of transition metal will split into two set of orbitals, T2G, which is of lower energy, and EG, which is of higher energy, right? Now when any compound, right, of transition metal, right, when on any compound of transition metal visible light will fall, right, it will cause DD transition, that is, it will cause electron promotion from T2G to EG, T2G to EG, right? And when visible light will fall on a transition metal compound, it will absorb light of definite wavelength, right? When it will absorb light of definite wavelength, some light will get absorbed, right, and the rest would be transmitted. It is due to the transmitted light that your compound will appear colored. Transition metal compound will appear colored, right? Let's take an example. In case of hydrated cupric ions, right? Hydrated cupric ions This hydrated cupric ions is a complex compound, right, which is formed between water, right, like here I've taken example water, which is formed between water and your cupric ions, right? We know that cupric ion is a transition metal. So complex that is formed between cupric ion and your water is your hydrated cupric ions, right? Now this hydrated cupric ions will absorb red light, right? It will absorb red radiation, right? Now when it will absorb the red radiation, electron transition will take place from T2G to EG, right? And it will transmit other lights, right? The other light would be, it will transmit greenish blue radiation, right? It will transmit greenish blue radiation, right? That is why transition metal compounds containing cupric ions, they appear greenish blue in color, right? Because cupric ions absorb red radiation and they transmit greenish blue radiation, right? Similarly, if we talk about cobalt 2 will absorb greenish blue light and they transmit red radiation. That's why they appear red in color, right? Cobalt 2 will absorb, right, greenish blue radiation, right, and will transmit your red radiation. When it will transmit this red radiation, the compounds of transition metal cobalt will appear red, right? I hope this is clear. So basically the transition metal compounds are colored. The reason is due to DD transition, right? And for DD transition to take place, you need to have half-filled orbitals. If you do not have half-filled orbitals, then your compounds will again appear colorless, right? So now we'll again look into the other, some compounds, transition metal compounds that are colorless. We'll look into the reason why. Right, let me just rub this off. This is very important. Many times this question has been asked in exams and competitive exams, right? Just understand this crystal field splitting. This is very important to understand, right? So now, okay, some compounds like Sc plus 3, right, and Ti plus 4, zinc plus 2, all these are colorless, right? All these are compounds containing these transition metal ions, right? Compounds containing these transition metal ions are colorless, right? We need to look into the reason why these are colorless, right? The reason is, if we talk about your Ti4 plus, Ti4 plus does not have any electron in the d orbitals, right? So this one, the electronic configuration of this is 3d0, right? No electron in d orbitals, right? Similarly, the electronic configuration for your scandium 3 plus is again 3d0. This is 3d0, and this one is your 3d10. Zinc is 3d10, right? Like I said, that for dd transition you need to have half-filled orbitals, right? And there should be electrons, right? When we say half-filled orbitals, we mean that you have like this kind of, if you have this kind of configuration, electronic configuration, where you have half-filled orbitals, and when two set of orbitals will split like this, right, then for dd transition to take place, you have electrons in one set of orbitals, right? Say this is your T2g, say this is your T2g, and this empty is your Eg, right? Now when visible light will fall on such a compound, it will absorb light and dd transition will take place. Electrons in this set of orbitals will be promoted to this set of orbitals, right? Now this is possible only when you have half-filled orbitals, right? And the other thing is, if you have completely filled orbitals. Suppose here I have electrons and here also I have electrons. When all the orbitals are filled, right, then electronic transition will not take place, because in that case you have no empty orbital where electron can be promoted, right? So half-filled orbital condition is required condition, right? And all the transition metal ions that have completely filled orbitals or completely empty d orbitals are colorless, right? Like I said, these are completely empty or filled. Like zinc is completely filled, 3d10, all the orbitals, right, all the orbitals are filled, so electronic transition again cannot take place, right? And if we talk about Sc plus 3 and Ti plus 4, you have no electron in the d orbitals. If you do not have any electron in the d orbitals, then electronic transition will again not take place, right? dd transition will not take place, so compound would be colorless, right? So for compound to show color, it should have half-filled orbitals, right? So that dd transition can take place between two set of d orbitals, right? I hope this is clear, right? Now if we compare with S and P block elements, right? Your S and P block elements are mostly colorless, right? What could be the reason? Because they do not contain d electrons, or they contain d electrons which that are completely filled. D orbitals are completely filled, right? Your S and P block element compounds of S and P block elements are colorless. The reason is no d orbitals. No d orbitals or completely filled d orbitals. Right? When you have no d orbitals, then this transition will not take place. When you have completely filled d orbitals, then again this, as per this condition, no transition will take place, like in case of zinc 2+. Right? That is why S and P block elements are colorless. Now they have S electrons, right? But these S electrons, in order to promote S electrons to a higher energy level, right, you need very high energy, which is not available in visible region, right? Because compounds are, these transition metal ions appear colored when visible light falls on it, right? And the energy of, or the wavelength of radiations in visible light is equal to energy difference between these two set of orbitals, right? So the absorbed energy equal to difference in the two set of orbitals, and d transition will take place and the compound will appear colored due to transmitted light, absorbed light and transmitted light, right? But this does not happen in S and P block elements, because energy required for transition, for electronic promotion for S and P block S and P orbitals is very high, which is not available in visible region, right? I hope this is clear. Thanks.